Hello and welcome to the very first video in the GRE Quantitative Fundamentals series. In this series, we are going to cover all the basic concepts needed for the GRE Quant section, and I'm going to try to keep each of these videos relatively short and focused on just one specific topic. I'm also going to be sticking to the general order of concepts that they lay out in the ETS math review, which I'll leave a link to that in the description, so if you want to follow along and see where we are, you can do that on your own. Each of these videos is going to start off with a brief overview of the concept and any useful formulas or methods that you need to know. We'll then take a look at some of the simple applications on the test and move up to harder and trickier examples. So if you already feel confident with a particular concept, I would encourage you not to just write off the video, but to skip ahead and test your understanding on some of the trickier questions before moving on. This first video we're going to be covering integers, which is a relatively basic concept, but one that is fairly crucial for a lot of problems and one that people do have some misunderstandings about. So let's get started. To begin with, and really the most important thing about integers, is that you have an accurate definition of what an integer is. Integers are not synonymous with the word number. I find that some people have this misconception. When the test uses the word number, they mean any of these things in front of you. So real numbers can include irrational numbers like pi, square roots. It also includes rational numbers like fractions and decimals. Integers are a smaller subset within rational numbers, and they refer only to numbers like whole numbers, 1, 2, 3, and so on and so forth, as high as you want to go. They also include 0 and they include negative numbers. So when you hear the word integer, or when you see the word integer used in a word problem, you need to immediately constrain your thinking to just these whole numbers, 0 and their negative counterparts. It's worth noting that imaginary numbers are not used on the test, so you don't have to worry about the square root of negative numbers, numbers like I that you may have learned about in high school. The GRE limits itself just to the irrational and rational numbers. Now, when you're dealing with the word integer, very rarely is it used by itself. It's usually used with another descriptor, like some of these words at the bottom: prime, composite, negative, non-negative, square, things like that. So a question will usually say, x is a non-negative integer greater than 4, or is a positive prime integer, or is a positive factor of 24, or something like that. To start off with, let's look at this problem here, which is a relatively easy application of this concept. So with this problem and all the rest in the video, feel free to pause the video at each question and take an attempt at the problem on your own. This question is asking us which of the following numbers, right, cannot be expressed as the sum of the squares of two integers. So when we consider these numbers, we're trying to figure out, can we think of two square numbers, numbers that are the square of an integer, that add up to each of our choices? So it's important here that it uses the word integer and not number. Far more numbers can be represented as the square of a number. For instance, 3 is not what you would think of as a square number, but if you square the square root of 3, you'll get 3. However, in this case, we're only concerned with the square of integers. So people will think often of 1 squared, 2 squared, 3 squared. So we're considering numbers like 1, like 4, like 9. And so if you work your way through, you should find that the only number that you can't represent as the sum of two squares is 24. Something that I do see some people miss, again, remembering that the word integer refers to not just positive numbers, but also 0 and negative numbers. 0 itself is an integer, which when squared gives you 0. So therefore, 4 would work, right? 4 plus 0 would be 4. Whereas something like 24, there is no way to represent that as the sum of two squares. Let's take a look at this second question, also utilizing the concept of integer. If an integer y is subtracted from an integer x and the result is greater than x, which of the following must be true? This type of question, I think some people will see this and intuitively come to the correct solution. Other people might pick some numbers. For instance, maybe you pick What if x is 1? What could y be in order to make it true? Um, Both of those will work to some degree. I think maybe the clearest way to solve this one would be to use an inequality. In this case, we might write it out like this. When y is subtracted from x, the result is greater than x. And again, like I said already, some people might be looking at this and thinking, well, the only way that that's going to happen is if y is a negative number, but we're going to go ahead and prove it. So the first thing we might do is subtract x from both sides. And if we do that, we're just left with negative y is greater than 0. And if negative y is greater than 0, we could either move the y to the other side, or we could multiply both sides by negative 1. So let's maybe do that. If we multiply both sides by a negative, we end up with y on this side, 0 stays the same, and the rule of inequalities is that the sign will flip. So therefore, we can prove that y must be less than 0. It's important to note that this question uses the phrase must be true, as opposed to could be true. Quite a few of these answers could be true, so if you just rely on intuition or picking numbers, you might come to multiple conclusions, but the only one that must be true is C. In attempting this problem, you probably notice that the word positive is attached to the word integers. So what that means is we're again constraining our thinking about the subset of numbers we're considering. We care about integers, but we don't care about 0, we don't care about negatives. Those are not in the realm of possibility. So we're thinking of integers like 1, 2, 3, 4, and so on. So if you attempted this question, chose some positive integers, decided to figure out which one you thought was bigger, you may have come to the conclusion that b is greater, and you'd probably not be alone, but you'd also be incorrect. Quantity b looks like it's going to be greater a majority of the time, and certainly if you pick a random set of two positive integers, like for instance maybe x equals 3 and y equals 2, what will happen? Quantity a will look like 3 squared, quantity b will look like 3 to the 4th, and of course 9 is less than 81, and so it would look like b is going to be bigger. However, when you're doing that sort of pick numbers method, you want to make sure that you're exhausting all the possibilities, especially the ones that behave differently. And in this case, when we think about the set of all positive integers, there's one that behaves differently, and that's of course the number 1. So for instance, if we pick x is 1, and it actually doesn't matter what we pick for y, it could be anything. Y is 10. Uh, Quantity a is going to look like 1 to the 10th. Quantity b is going to look like 1 to the 12th, and 1 to any power is just 1, and so the two quantities will be equal. And so no matter what you had picked for y, so long as you had checked what happens when x is 1, you'd find that the quantities were equal, and these two situations together are enough to conclude that the correct answer must be D. So again, this is just pointing to the importance of making sure you know what the subset of numbers are that you're allowed to choose from. In this case, positive integers include 1 along with all the other positive whole numbers. We're going to look at two more problems here that are definitely a little more tricky and really illustrate how important the word integer or some of these words around it can be when solving a problem. So if you attempt this problem and you take it either algebraically or if you decide to pick some numbers, what might occur to you is to pick some easy positive numbers, like for instance, if you decide on c equaling 1, you'll very quickly find that b must be 2 and a ends up being 6. And so if you do that, quantity a will just be 6 plus 2 plus 1, which will be 9, and quantity b will be much bigger, right? 12 plus 2, 14. So we already have a situation where quantity b is greater than a, but because the numbers that we can choose from include all integers, if we picked 0, the quantities would be equal. If we picked negatives, quantity a would be the larger quantity. And so of course the result is that the answer must be D. However, if I go ahead and change this question to positive integers, and you might want to just think about this and come up with an answer for this one as well. what you'll find is that the way that these are set up, if A, B, and C are positive quantities, without a doubt, C is going to be the smallest quantity, and then B will be twice as large, and A will be 6 times as large. And so when we look at these quantities, no matter which ones you choose, whether it's the same as last time, 1, 2, and 6, or you pick a different set of positive integers, you're going to find that B is greater every single time. It really was 0 and negatives that allowed us to find that exception for D to be the correct answer. This question takes a little bit more work to get through, but not terribly confusing. T is a list of 50 different numbers between 0 and 100, and X is greater than 80% of those numbers, Y is greater than exactly 40% of those numbers. So X and Y are both numbers hemmed in by the numbers in the list. So what might this list look like? Well, it just has to be 50 different numbers between 0 and 100. One of the easiest lists I can think to generate would just be 1, 2, 3, 4, 5, all the integers from 1 to 50. And so if you do that, what ends up happening? Well, X needs to be just above the 80th percentile, which in this case would be 40, and Y needs to be just above the 40th percentile, which would be 20. So in this case, we'd have something like X would have to be around 40, maybe let's say 40.5, and Y would end up being around 20.5. And so the difference between those would leave us with X minus Y equaling about 20. So in this case, it looks like quantity A could be greater than quantity B. Now, if you made the mistake of reading the word number as integer in the problem, you might have thought, well, this set here, 1, 2, 3, 4, 5, is as closely packed as I can make my list, which means the difference between X and Y can't get any smaller than this. But of course, that's not quite true, because it's not necessary that we just pick integers. The question only says numbers between 0 and 100. So what if we picked a bunch of decimals or fractions? Very, very small numbers. We could pack them really close together. And in a case like that, X and Y can be really as close as we want them to be. And so of course, quantity B might be the greater quantity. Therefore, D would be the correct answer. So if I do go ahead and change the problem to read as 50 different integers between 0 and 100, then precisely what we were talking about before will happen. The closest you can pack those numbers is something like 1, 2, 3, 4, right? Just a list of positive integers. And when you do that, the closest you can get X and Y, or the smallest you can make the difference between X and Y, which is what quantity A is asking for, is 20. And so in that case, A is always going to be greater than quantity B. Alright, and that concludes this first video in the series. If you have any other questions or comments or ideas for videos you'd like to see made, leave them down below. Otherwise, I hope you'll join me for the rest of the videos in the series as I continue to put them out. Thanks for watching.